Hello and welcome to what I hope will be a series of videos about various space-related graphical effects. So for a game I'm working on, which is set in space, of course I need to display various planets, and some of them might have an atmosphere. So if you've also been looking for this kind of effect, you will have come across various implementations. Some of them take the more realistic approach, like the one you see on the left. This is based on atmospheric Rayleigh I don't know how it's pronounced, scattering, which through numerical approximations tries to simulate what happens to the light when it hits the particles in our atmosphere. And as you can see, it's much nicer and fades very well into the outer space when you come close to it. Whereas the one on the right is based on a Fresnel type of rim lighting, and it's much cruder to see, I think. But it's also much simpler to implement, and you can customize it quite easily. So the reason I'm doing this video is because I spent countless hours trying to make the Rayleigh algorithm work, and so in this video I hope to show you some of the common mistakes that you can avoid if you follow these simple tricks. So in order to explain how the effect works, I will be using the universal render pipeline. And so if you're interested in the proper Rayleigh atmospheric scattering, please skip ahead. If not, I will start by showing how the simpler version of the scattering or the atmosphere works. So this is the shader I've used. It's basically using two main principles. We have a Fresnel node for the outer rim, and then another Fresnel node for the inner part of the atmosphere. So here I've defined a property for the intensity of the rim effect, which I've set to 8. I multiply it by the same value in order to strengthen the value, because of if I simply create if I simply add a larger number, you can see that the effect becomes very much thinner. So in this way, I keep the same in the same size, so to speak, but I make it brighter by a multiplication. Here we have another Fresnel node, but with a much lower intensity, 0.5. I then pass the value through a 1- node to get rid of this dark area in the center, and I divide it by a number in order to make it less bright. Then we have this series of nodes here. Basically, this is just to determine which part of the sphere will be lighted and which part will be in the dark. You might wonder about this node here. I call it the light node, but in reality it's a subgraph, because Unity doesn't have a node that just tells you what the direction of the light is. So I created this subgraph, which is based on a custom function. You can see the code here. Basically, I have added this define here, if shader graph preview, in order to hard code a direction for the light, because when we are in this shader graph editor, we don't know yet where the light will come from. But when the shader will run into the proper game mode, you can get the results and the values from this built-in Unity function called getMainLight. This results into a structure that tells you the direction and the color. And then I've defined two outputs with the same names. You don't need to declare them again. You just need to assign the values from the structure to direction and to color, and then just plug in the values into the output of this subgraph. And then you will have the direction in this node, which you can use for various other shaders as well. And okay, so the dot product will tell you what part of the sphere is lighted and in the dark. Then I just clamp it for good measure, and then here we move to the main part of the shader. We basically add the rim lighting to the inner lighting. Again, a clamp. I don't know how much these are necessary, but I don't think it hurts that much. And then when you have combined the two atmospheres, the two lighting effects, you should multiply them with the the results of the dot products in order to shadow the part beyond the light, and then multiply it by the color here, which is again is a parameter that I've defined here as an HDR color, just a bluish kind of value. And then you can plug it into the emission value so that you can use it as well with some blur filter, maybe to give it a bloom effect. The workflow here, well, I've left it to metallic. I just changed the blend mode to additive instead of alpha, because we want the bluish part of the atmosphere to add to what's behind, to the color of the planet. And of course, in order to make this work, you should use the transparent workflow. Okay, regardless of what effect you're using, you should have two spheres. That's what the approach I've been using it for the effect. So I have one sphere for the surface, you can see here, and that is the atmosphere on the right. The idea is that the atmosphere sphere should be slightly larger. I've used 1.025 as a value, whereas the sphere for the planet itself is just one. Let's see how well it looks. Okay, so again, this is the atmospheric scattering, the Rayleigh, and this is the atmosphere through the Fresnel node. And as you can see, it doesn't look terrible. You can change some of the values here. For example, the intensity and the brighter part of the atmosphere, and also just change the tint of the color if you want to get that alien feeling. You just change the color and maybe the intensity of the planet. So that was it for the Fresnel implementation. Let's have a look at the proper atmospheric scattering. So I've based my own implementation of the atmospheric scattering on this Shader 2 example by Dimas Skeider-Dragon Lenman. So if you're reading this, thank you for your implementation. This Shader 2 example is itself based on another implementation, and at some point in the chain, I think we will go back to the original O'Neill paper and all the various implementation of it. The principle is similar, but there are some things that you need to take into account when you want to convert an effect that is demonstrated on Shader Toy and apply it to Unity. Of course, you have to look at the license, because not all of the shaders on Shader Toy can be used freely. This one in particular is based on the MIT license, and it's very well commented and explained, as the title says. So with the MIT license, it means that you can freely use it in your own commercial project, as long as you credit the author and include the original license. You can even test it from space by changing one of the parameters here and recompiling it, pressing the play icon here, and yes, so as you can see, this is what it's supposed to be like. So that's the reason I chose it, because in this way I would know how it looks like and when I was testing my own implementation. So the idea of the shader, if you have read the O'Neill paper, is basically revolves around considering what happens to a ray as it intersects the planet. So as you can see, there's this huge functional calculated scattering that does most of the work. There's the first sphere intersection. If it doesn't hit the planet, then of course it will have to be black. Otherwise, we see what happens to the ray. Does it hit the planet? Does it hit the atmosphere? And so on. So there are these 4 loops. There's one outer loop and another inner loop, which basically calculate the numerical approximation of what is happening to the ray according to this step parameter, and that you can define in order to indicate how much complex and accurate you want the calculation to be. What matters is that at the end of the day you get a final color, which is the actual color that is used for the atmosphere. But in Shader Toy, the final effect is being rendered on a 2D quote. No, there is no actual 3D geometry. It's just based on a 2D flat polygon. So when you need to include in your calculation the view direction, you actually are going to consider the UV coordinates of the texture, not a ray that goes from the camera, from the screen, from the world position of the vertices to the camera, but you're going to use the UV coordinates. Okay, so let's have a look at the atmospheric scattering shader, the proper one. Okay, so this is the shader that I have implemented again in URP. It looks very daunting at the beginning, but it's not that much difficult. So everything revolves around this custom function, which is basically that huge function that you will see in the shader toy example. So basically we are passing all the values that the algorithm requires to work. For example, the position of the camera, the view direction, the light direction, again using the light node I've described for the other Fresnel based implementation, the intensity of the light. These are all parameters that are needed by the algorithm to make their calculation. For example, how many steps you want to use in order to make it more or less accurate, and some other parameters that I've also added in order to make it possible for you to change the results in a non-realistic way. So the first and most important thing is the camera position and the view direction. So the algorithm that is used in this shader works assuming that the dimensions of your spheres are in meters. You know, the actual radius of the Earth is used in the implementation as a reference point, and all of these values are in parameters such as these ones, for example, atmosphere radius and planet radius. So these are actually meters. So you have 100,000, and you have here 371,000 meters, which is the radius of the Earth in meters, and therefore you have to plug these values in the algorithm for it to work. However, the sphere that I'm using here, this is the sphere that is as the proper atmospheric scattering algorithm applied as a scale of 1. So you need, first of all, you need to convert between units and meters, and that is what is happening here. So you have this node camera, which returns you the position of the camera. That is where from which position in space you are viewing the planet, and I'm multiplying it with a conversion factor, which takes the value from this other multiplication here. Here we have a planet radius and a sphere radius unit. So planet radius is the 6 million value here. The sphere radius is the radius of the sphere in Unity units, which is 1. And so you will get a very small value from this multiplication, but we can use that to convert from the camera position and make it so that the position it's using to calculate your viewing point is calculated in meters, actually, in where you will be in space if you were looking at a sphere of 6,300,000 in radius. So that is the reason of this conversion, and you need to do the same for the position of the planet in the world space. So we have this object that tells you the position in world units, which in this case will be 0, 0, 0, but in case it's not, you also need to multiply it with this set of nodes, and again you will translate the position in meters into the shader. And I'm also using to pass these values to the shader, as well as all the other coefficients that the algorithm needs. So with these two nodes here, with the camera position and the position, you have handled the conversion between meters and units in world space. So instead, for the other important parameters, view direction, you need to do something different. In a shader toy and other quad-based implementation, they are assuming that the view direction is basically coinciding with the UV coordinates of the texture. But in this case, we actually want a ray that goes from a position on the sphere, which is the result of this node. This will give you the x, y, z coordinates of a point on the sphere because it's in the world coordinates. And we want a ray from the sphere to you, which in this case you will be the camera. And so you subtract the two values, so a ray from the sphere to the camera, and then normalize in order to get a unit vector, and which you can plug in into the custom function here and to the view direction. Another part that I have added to the shader is to calculate the size of the atmosphere automatically based on the dimensions of the atmosphere, because I didn't want to change the scale for every planet that I had. So in this case, both the surface sphere and the atmosphere sphere are all size 1, but the atmosphere sphere has this normal extrusion effect applied, so it will be a little bit bigger when you apply the shader. How does it work? So again, we have the normal vector here, and we need to multiply it by a value that is also depending on the size of the planet in meters, the 6 million values here, and the sphere radius in units. So in this case, the default value is 1, but you might have cases where the planet, like for a moon, it might be smaller than 1. So you want everything to be proportional. I'm multiplying this by another intensity value here and the radius in order, if you want to make the effect stronger, but of course in this you lose the realism, no? Which is also what you are looking at here. This atmosphere effect has been made more intensive. In fact, it will look very different if instead of the 5 I've used here, I would use 1. You know? In fact, it almost disappear, and you can look at. There's a very faint effect that you can see on the rim of the sphere, but you know, we actually want to be awed, I think. No, we want to be impressed by space and everything else. So I think 5 would be a better choice. You know? At least that confirms my expectation of what the atmosphere will look like in space from movies and so on. So it doesn't have to be as accurate as the implementation of the algorithm. We want to have a good effect, which is nice to look at. But I still think that the scattering is a better choice than the Fresnel, because it gives us a much softer result into the inner part of the sphere. So that's why I would advise to use this implementation instead of the other one if your hardware can handle it. Okay, so back to the shader here. So we were talking about the intensity of the atmosphere, and again, what you need to do then is to multiply this increment to apply to the normals, and then add it to the position of the vertices. No? And you will get a value here that is in world space, and that needs to be transformed back from world to object space through this transform node, and plug it back to the vertex position node. And there you have it. So the atmosphere will be larger depending on the size of the atmosphere. You can see that if we say that instead of 60,000 meters, it's 9. It should become bigger, maybe 250,000. Yeah, you can see that it starts to become larger. But you can achieve the same effect with the atmosphere intensity in order to make it larger and larger. I added another scattering intensity effect in order to control the extent of the effect on the inner part of it. So if you want it to be more subtle or not. In this case, a value of 0.2 will be good. All of these values here come from the implementation that you see on Shader Toy. These are values that from that shader toe implementation, they come from the original implementation of the algorithm. Basically, they refer to the absorption of the light waves according to the RGB colors. And you can find such values for other planets. Indeed, I have here other values that I've found on a paper that were trying to, in which they were trying to apply this, to calculate the scattering effect for Mars. Let's see if I can show it to you. Let's duplicate this. Okay, so let's hide the other implementation here. Okay, so first we need to apply the surface of Mars, actually. Okay, and this is using the atmosphere from Earth, but we want to use this atmosphere from Mars, which we applied here to the other sphere. The values of the scattering are different, and I've sourced them from another paper. I can add the link to the description, but these are the values that I've been using for Mars. And of course, it might give you an effect that is a bit different from what you're accustomed to see in games and movies. You can see that it's almost gray instead of maybe the reddish or yellowish tint that you might expect. Of course, Mars has a very thin atmosphere. I think less than it's 0.5% the atmosphere that the Earth has. So even this is a great approximation of it. Some other customization that you might want to apply to your shader is to introduce a parameter to change the color of the atmosphere. So you could find the correct coefficients, but probably nobody's going to notice that. So simply introduce a parameter like this, and then you can tint the values of the color used for the atmosphere, and you can get a nice looking alien atmosphere. The calculations for this is actually done in the shader itself. So the parameter goes from here to the main function, and then directly in the HLSL code. And one other thing that you want to look at is the disabling the Z-write. So in URP, as far as I know, there's no easy way, or not yet a way to disable these shader features like Z-write off, call front, those things that you might be used to do when in the old days when you wrote actual code. So one thing that I have done is to place the atmosphere sphere in a special layer called Z-write off, and then in your pipeline settings add a renderer feature that basically doesn't write depth, because otherwise if it is enabled, then you see that depending on the depth test that is used, or whether you're writing depth, you can get some weird results. So it's best just to not write depth and place the transparent sphere on this layer itself. And you can do that by using the layer mask and adopting these features only for the layer in which the atmosphere is rendered. One more thing is for the light. So here is what happens when the light also lights the atmosphere, because in our shader we are assuming that how it looks is based on the calculations that are performed inside. So you don't want Unity's default lighting to change it. So this is what happens when instead Unity also lights the atmosphere. So you can see it looks very weird, and there's this weird washed out color. So it's best that you don't use Unity's default lighting for the atmosphere. And you can do that by using this culling mask, and yes, it looks fine now. Okay, that was it for this video. I hope you enjoyed it. Let me know what you think. Does the atmospheric scattering shader look better than the Fresnel, or you prefer the other one? If you would like other videos about space-related graphical effects, let me know in the comments below. Thank you for watching so far, and I hope I will see you next time. Bye.